Our next presentation, we have a tag team here. We have Sakti and Brian. These folks are from Arista. They're going to be talking about a lot of things involved in high-performance media networking. So because they had so much to talk about, we gave the two of them a full hour to go through and talk as much as they want. And I'm sure we're going to have some questions at the end, so we'll leave a little time for that. This should be a pretty good deep dive into some of the cool things that is going on in the world of topologies for 2110, and then network orchestration for moving those high bandwidth signals around in a network. So take it away, Sakti and Ryan.
So when we're talking about architectural options in the SMPTE 2110 workflow, there are a bunch of questions that, at least when I'm speaking with customers, I have to ask about. What switch platforms are we going to use? Specifically from a bandwidth perspective. Will we be taking advantage of 400 gig? Will we be taking advantage of future 800 gig? Do we need to think that high in bandwidth? How much UHD content will you eventually be migrating to? How much 3G content? All of this impacts the flow stitching, the flow paths in the system. We also need to understand how resilient will the network be. Do we need SMPTE 2022-7? Will we be using a monolithic system? So one big chassis? Will we be using a distributed architecture, more of a spine leaf architecture? Will we be using layer 2 multicast or layer 3? We should always use layer 3, and I'll be going into reasons later on as to why layer 2 multicast might be a problem in some systems. Will it be a separate red and blue network or a purple mesh network? Will we be using ASM, so star comma G joins, SSM for S comma G joins? Or will we be using routed network orchestration, which we'll be getting into later? All these questions are really crucial for any SMPTE 2110 deployment. These are the typical topologies, at least that I see today. So if we start at the far right, the spline monolithic, that's where everybody just connects all of their devices directly into those two big switches. That might sound easy, and it can be easy from a configuration perspective. Then you have to consider cabling, home running devices from all over your facility back to that one monolithic system there, or two monolithics for red and blue, obviously. Then in the middle, we have the spine leaf architecture. That's very common nowadays. You have a spine of some sort and a bunch of leaf switches distributed throughout your facility, so you don't have to home run every single endpoint directly to the spine. It also provides, assuming the right platform has been selected, a lot of east-west horizontal flexibility, scalability. I'm always into scalability. I always want to make sure that on day one, my system satisfies what I need to support, but then days later, years later, I still have that support. I can still expand horizontally east-west from the network. And then there are purple networks as well, the ones on the far left. These aren't as common right now, but I do see them popping up more and more often. We'll review why these networks might require more intelligent management from an orchestration and broadcast control workflow. Now, there are a lot of considerations we have to take into account, and again, in these workflows. The dynamic nature of our broadcast solutions. We're going to be outputting a lot of multicast signals at a lot of different bit rates throughout the system. There will be many terabits per second of traffic going throughout this network. Now, we're going to, in the top architecture there where we have spine leaf, we will have to take care of the bandwidth going between those links. I'll be providing some information about that later on, and then same with the monolithic approach there where, assuming that your switch fabric is non-blocking, and what I mean by that is if all interfaces running at 100% usage, you could forward them from, throughout the fabric from input to output, full utilization of bandwidth. Now this again comes really in handy. We need to know about this stuff because there are endpoints that output or receive a lot of multicast traffic. Some endpoints now have 100 gig interface connections where you might have 8 UHD signals going, being received or being sent out on each one. So there is a lot of bandwidth going through these systems. And again, these systems are only growing. I don't know many systems that are scaling down in size once they've been deployed. They're only growing in size. Okay. Now, in order to make recommendations about topologies and things like that, we have to have a somewhat of an understanding of multicast itself. Now, I hear about layer 2, layer 2 broadcast domains, whether it's going to be for just an audio deployment. I've even seen some people try to deploy a layer 2 network for for their entire architecture. And when I say layer 2, what I mean by that is all of the endpoints are going to be connected in the same subnet, same VLAN. All the source addresses of all your devices are in the same subnet. That can be damaging if your multicast address assignment is not done appropriately. And it's important to understand that because this all impacts the topologies that you're going to eventually decide upon. In this example here, I have, say, 3 cameras all outputting what looks like to be unique multicast addresses: 239.111, 238.111, and 237.111. Assuming all those devices are in the same VLAN, there's a side effect of this called aliasing. Now, all of these addresses here will map to the same multicast address in the network. So what that means is if you have a receiver who's requesting just one of those groups, they will actually receive all 3 of those groups. And there's no way of stopping that. There's no way of stopping that in a layer 2 network. So not only is the multicast address assignment very, very important, but understanding the nature of multicast in layer 2 and layer 3 environments is equally as important. Also in layer 2 multicast, there's this idea of a querier. An Igmp querier is what sends out the general queries for that VLAN saying, hey, who wants whatever multicast address? This is really important to understand because any interface that receives what's called a general query, so who wants what, essentially, that interface that receives a general query will, in this case, will become an mRouter port. So these are labeled, these are shown on the drawing there. Part of the layer 2 multicast standard is that any mRouter port floods multicast to the querier address. And again, this cannot be stopped. So we can see why having a spine leaf, a hub and spoke architecture, and using layer 2 multicast, or having layer 2 in this system, the entire system, from spine to leaf, is a really, really bad idea. Now, there might be some exceptions to it, of course. There are always exceptions to every rule. But when we're going to be talking about, again, heavy-duty multicast in your system, having all this flooding up there is just not a good idea. And then it depends also on where the querier is actually placed. Is the querier placed on the spine, in which case it floods up, or is it going to be placed at another leaf switch by accident or by mistake, where you get a cascade of flooding? So everything floods up to that spine there, and then everything floods back down from that spine down to that leaf. These are just instances of really where, again, having a system that's entirely layer 2 can be a very, very, very significant problem. Now, there is a solution to this in typical media environments, typical SMPTE 2110 environments, and that's introducing layer 3 multicast, separating the VLANs, using and taking advantage of PIM, which is protocol independent multicast. Commonly used in SMPTE 2110 environments today, extremely common. The majority of these systems rely on these sorts of protocols today. And what this does is it breaks away. It limits the blast radius, essentially. If you have a layer 3 network, you won't have all this intermittent flooding or accidental flooding of your endpoints, potentially up to from leaf to spine, or to all of your endpoints in that subnet. That's why a lot of customers now are migrating into an entirely layer 3 system, even down to the endpoint itself. But with PIM, with dynamic multicast protocols, comes some issues. And the issue there is that these protocols are not bandwidth aware in any way. So what does that matter? Well, that matters because these protocols don't know if 239.111 is a 10 gigabit per second stream or a 1.5 gigabit per second stream, or if it's a small audio stream of a few megabits per second. It does not matter. And these protocols also don't know the bandwidth of the links themselves. So they don't know if it's a 100 gig link that it might be traversing, or if it's a 10 gig link that it might be traversing. And they don't know how much bandwidth is actually being assigned across those various links. So I like to ask this question when I'm speaking with customers is, using this drawing looking at the drawing on the bottom here, is this network considered a non-blocking network? Can I send the 320 gigabits per second from switch 1 to all the way to switch 2, all those other receivers there? Some people say yes, because, well, 4 100 gig links, 4 times 100, 400, is greater than 320, non-blocking. That's not entirely true, though. And that's because the hashing algorithm, what I was describing before, is that PIM is not aware of the bandwidth. And there's a hashing algorithm that's used to essentially assign which of those interfaces a specific multicast flow will traverse from one switch to another switch. This all impacts your topology, whether it's, again, a spine leaf system or just 2 switches cascaded together, 2 switches connected to one another. So in this instance here, sending 320 gigs over those 4 links, I could very well have one link that reaches 100% and kills everything else on that link. But then you might say, well, what if it works today? What if I make it, I strategically assign the multicast addresses, next hop addresses, things like that, so that it works today? Well, that might seem like it's a really, really good idea. But then what happens tomorrow? What happens when you start changing some of the bandwidth of some of those multicast flows that are going over from one switch to another switch? What happens when you add a few more multicast flows? This sort of, the dynamic nature of broadcasting calls for, a better way. It calls for, in leaf spine environments, whenever essentially you are utilizing a significant percentage of the bandwidth between these links, between these 2 switches, something better. And we'll get into that again shortly. Now, the multicast hashing algorithm that I was referring to, there are a number of things that go on that go on there that are used to judge which link you'll actually be traversing. That's based on the multicast group address, the source address, and the next hop, starting from your receiver, going back to your source. It'd be impossible if you have tens of thousands of multicast groups to strategically place them, to strategically assign them so that the hashing algorithm works exactly how you want 100% of the time. Now, we have I have a little media entertainment lab with some devices just outputting 30 gigs, for example, 30 some odd gigs across a spine leaf. Now, again, I'm not close to saturating the bandwidth here, but I did want to show this because it shows the uneven distribution of multicast across just a very, very, very simple spine leaf system or hub and spoke system. We can see that it's very unevenly distributed and that one of those links, or one of those links is utilizing approximately, half of the bandwidth, and 2 of those links is using probably like 80% of the bandwidth. And it's not symmetrical either. So going from the senders to the spine is not equal from going from the spine down to the receivers. This sort of inconsistency can be seen even with a small amount of bandwidth of 30 gigs. Think about what happens when we increase this to have flows of 10 gigabits per second, and when we have hundreds of flows in your systems. Now, some might be able to say, just throw more bandwidth at it. Just throw more bandwidth. Upgrade to, say, 400 gigabits per second. Upgrade to those really large connections. But then your leaves end up having more bandwidth associated with them. Essentially, if you're ever going to be utilizing so much bandwidth that you might use over, say, 50% of your network links, that can cause hashing problems. But again, this all has to do with if it's running in steady state. What happens when a link goes down? So this shows that a link went down at some point. And what happens here is that when this link went down, 51.1 went down, the multicast flows that were traversing that link got redistributed across all of the other links. And this is something that we really have to take into account as well. Not just what happens in steady state when all the links are up, what happens when you want to do maintenance, right? What happens when one of the links just happens to go down because there might be a fiber cut or an optics failure, something. All those flows get redistributed across the other links, and then the hashing algorithm gets re-implemented, but instead of going through 4 links, now there's only 3 links. Again, all this can cause a lot of problems in a system depending on what your topology looks like. Again, most people are now, most systems are going to a spine leaf system, spine leaf architecture, and they should. It's more scalable. East-west scalability, it'll be very hard if you buy the right switch to fully saturate all of your links there. Very, very difficult. Then we get into purple networks, where it's fully meshed. All the leaf switches are connected to all the spine switches. It's a typical data center topology, and there are customers who are looking into this right now. Now, this presents its own sets of challenges, and I'm trying to show that here. I have a camera that's outputting, or a sender that's outputting two signals, the red signal going to leaf 1, the blue signal going to leaf 2. And I have the receiver as well that's requesting obviously the red and the blue as well. Now, there is no guarantee in an IGMP and PIM system, well, there are a couple problems here, but there's no guarantee here that the flows will not take the same spine. So there's a very good chance here that when I'm sending that from the camera to that receiver there, that both the red and blue will take spine 1. There's hashing algorithms all over the place in spine leaf architectures. And again, it's very, these are the right architectures to go with spine leaf, but it's something that we all have to be mindful of. Now, besides this one interesting caveat of the possibly introducing a single point of failure, which no broadcaster wants. That's why you have 2022-7. So you don't have a single point of failure in your network. But there are other issues as well. I don't have it shown here necessarily, but envision a scenario where you have, say leafs 3 and 4 here, which also have other receivers connecting and wanting that same camera. There's the possibility that this sender will exist in multiple spines. So you're essentially, duplicating or quadrupling or however many spines you have. You might be really increasing the number of bandwidth unnecessarily throughout your network because they might take different spines. And it's really important to understand all of that when we're going over topologies. Now, there are some ideas learned, some ideas that we've learned. There are obviously some questions that, we have to ask. Again, how do we design a clean network? How do we design a very clean network such that it works today and it scales tomorrow? It's really important. It's a really important question to ask. I like spine leaves because they're clean. Again, it's very easy to implement just a standard unicast routing protocol like eBGP to allow for the unicast routing. And then we can get into some of the more exotic things later on, like, again, which we're going to be discussing, orchestration. Take advantage of 400 and 400 gig switches now. They are being used in SMPTE 2110 deployments today. But also think about other size systems as well in the future. Think about maybe utilizing 800 gig as well. Seeing if chassis, for example, modular switches that support 400 gig today support 800 gig in the future. Don't cascade switches going one to many hops. That's bad news. I've never recommended. Again, this goes back to the idea up above, having a clean network, keeping everything 2 hops away. Leaf, spine, leaf. Use layer 3. Don't have layer 2 network. Don't have layer 2 unless absolutely necessary, going from spine to leaf. We don't want to flood multicast unnecessarily. Layer 3 is really helpful, and it reduces the size of your blast radius as well. Understand your network. Do you need a SMPTE 2022-7 environment? What do you need to satisfy your redundancy needs today? And finally, will you need orchestration? All the ideas I've been discussing today with regards to topology and the hashing algorithm, it all comes back to how do I deliver my multicast from sender to receiver efficiently and in a redundant fashion so that I know my signals, I know my content is going to stay up all the time. That's what we want. We want 100% uptime. And a way to achieve that sort of security is through network orchestration regarding multicast, in a multicast workflow. And now I'll give this over to Sakti here to review what that means. What are the advantages? Why do we want to have a spine leaf system with network orchestration? Thank you.
Cool. Thank you, Ryan. So one of the key aspects that we need to consider while moving into a spine leaf architecture is multicast orchestration. What is orchestration? Orchestration is a systematic provisioning of multicast routes using a centralized controller in an IP network so that we can set up multicast routing between senders to receivers. Some of the key drivers, while the systems are migrating to are looking up to orchestration, are providing bandwidth protection and allowing the multicast routes on the switch to be programmed in a predictable and deterministic manner, to facilitate with scale and performance, and to infuse reliability and security to the multicast workflows, and to provide flexible architecture, and also aid with monitoring and visibility in the future. So to start with, one of the key primary drivers that led people to start looking up to orchestration was to provide bandwidth protection and determinism. As Ryan mentioned, we saw that PIM and IGMP was not built keeping bandwidth in mind. So the way the protocol was architected was in a way that the route choices were made in an undeterministic pattern. There was no load balancing, and there was no information about bandwidth while the route decisions were being made at the network. With the lack of bandwidth and with the lack of topology awareness, it maximized the chances of failure domains in the network. So, for example, Ryan did talk about considering a multiple link network as a non-blocking. If you look at the example on slide, we have 3 links with 300 Gbps total. And if you're using PIM for multicast routing here, it is not going to look at the bandwidth of every link to make a decision of whether to allow route programming on this link or not. It's just going to dump the routes and allow the network to take care of routing. So to prevent oversubscription or to reduce the failure domains, what's important is that it's important to have a centralized controller where the controller has end-to-end topology awareness, and it can aggregate the topology and bandwidth information outside of the network. So when there is an external controller integrating with the network requesting for multicast flows, this centralized orchestration can make the decision of what's routed where, what does my topology look like, what's the bandwidth capacity in my topology, and if I can provision those multicast flows or not. One other feature that we need to consider while picking up orchestration solutions is that even if the primary drivers were bandwidth protection and to provide deterministic programming, the other key thing that we need to think a bit more further is the resiliency and security of the network. So after programming the network with a deterministic fashion and providing bandwidth control, we need to assure that the life cycle of that multicast flow on that network is also secured throughout its lifetime. So if there are any network link failures, the orchestration layer should be able to expose that to the broadcast controller or to the operator so that they can make priority-based decision during their workflows and choose to reroute things as needed. With SDN orchestration, what we can do is that since it has the network topology information and it knows where multicast flows are provisioned at every hop, it can coalesce these two information and expose in a simple fashion to the broadcast controller of which flows are impacted because of which network failure. So we can see that in the diagram we have a leaf-spine leaf network with a couple of receivers in the receiver leaf and one receiver in the sender leaf. If the uplink to the spine from the sender leaf to spine is impacted, then the orchestration layer will be able to expose just receiver 2 and receiver 3 as impacted without having to worry about receiver 1. The orchestration solution should also be able to provide the operator with a choice of picking and choosing which flows do I need to recover at the time. We saw that PIM and IGMP does not consider any priorities, it just automatically reprovisions flows. which is not advisable because during your workflows or during your operations, the priorities of the multicast flows in the network can change. So if you have 9 flows and like all of those 9 flows are impacted because of a network failure, then the operator can choose to just reprovision 3 of them depending upon the bandwidth availability in the network. So, like in essence, the SDN orchestration solution should be able to provide the operator with a choice of what needs to be recovered and what can later be fixed. Another protection or another shortcoming with multicast senders can be some of these multicast senders are bursty. So there needs to be appropriate level of security configs that we need to apply at the sender interface, so that we can smooth out these the traffic that's coming from the bursty senders. During the lifetime of the orchestration solution, we should also be able to provide a highly redundant service, and not only just a highly redundant service, but also provide data redundancy. So in case of any failures, the network traffic on the switches is preserved. So the orchestration solution should also be intelligent enough to expose user errors with respect to misconfigs, so that the routes that are pushed by the orchestration layer does not get overwritten and the traffic is not impacted because of user errors in the network. And all of this is just to completely eliminate any failure domains that can occur, either from the broadcast controller, from the multicast sender side, or from the user side. So as more and more workflows are migrating towards IP and the user scales with their workflow requirements, the orchestration solution that we pick should be able to seamlessly adapt and grow with as the topology grows. We have few customers who start with a smaller network for testing and trying out orchestration, but like they plan for a larger network a year or 2 years down the lane. The orchestration solution that they are picking initially should be able to adapt to their increase in multicast scale or the increase in the number of switches that they are controlling over the lifetime. Sorry. So when we are picking an orchestration solution that can program the multicast routes, it's important that the solution can provide path diversity to the multicast routes in the network. With PIM and Igmp, there is no predictability or determinism, so there is no assured path diversity that is present. So there is a very high probability of most of the multicast flows getting concentrated on a single link, which will increase the failure domains. But with orchestration, what we can do is we can ensure that there is good load balancing for multicast flows, and there is intelligent programming of multicast routing across the available switches. With flexibility in orchestration, it enables us to scale like an orchestrator layer or network orchestration layer to adapt across workflows. So we know that with orchestration, you can have static multicast routing and dynamic protocols coexist in the same network, but it can also enable us to communicate between zones. We see that some of the customers would like to control the production zone with IGMP and the orchestration zone with a network controller. In such cases, the orchestration solution should be able to enable a seamless flow of traffic between both of the zones. There are also necessities for certain customers where they want to deploy SMPTE2110 networks in multiple sites, and they want the network control solution to facilitate the traffic between these sites. The orchestration layer should also be able to support these deployments. So with respect to scale and performance, the network control orchestration layer, it's a simple software. It's going to be a software solution by the end of the day. But what's more important is that the solution is architected right, so that the performance that it is delivering at a smaller scale or a smaller subset of flows is consistent and predictable even for a larger scale and the larger subset of flows. So the time taken to program a single multicast flow should be as predictable as programming large salvos. And an orchestration solution architected right will be able to provide consistent performance at any scale and at any topology. So one of the interesting conversations that we have been having is that will the orchestration solution be able to enable monitoring and visibility into what's happening with the network? As broadcasters are buying more and more IP switches, there is inherent doubt about switches being a black box. So what can we do from the orchestration layer to enable them to see workflows end to end and what's happening in the network? With orchestration, we can provide a relatable experience for the broadcasters so that, for example, we can add mnemonics to identify the multicast streams so they don't have to worry about identifying streams with the multicast IP addresses. And another key aspect with orchestration is that if I'm trying to program a route, the response that I'm getting back should assure me that the route is existing on the switch and the traffic can be enabled to flow. Broadcasters are used to getting tally-based feedback from the system, so as they have a take, they would like to see a confirmation of action for the take. So the orchestration solution should be able to deliver these real-time tallies as well. So as they are requesting the network to program a flow, they should be able to get a confirmation of action that the flow has been succeeded or it has failed. So in summary, everyone starts with orchestration solutions to provide bandwidth protection and to provide determinism, but we need to demand more from orchestration. We need to think about broadcast workflows and how to create a more relatable experience for the broadcast operators with network orchestration. So IP has multiple facets that we can infuse and make it malleable so that the broadcasters have a seamless experience as they start with deployment, orchestrating the multicast flows, and till monitoring.
All right, thank you very much. We appreciate this. If anybody has any questions now, we'd love to handle them.
Yeah, the orchestration, this software now, is that what you guys do?
So Arista has an orchestration service called Media Control Service, MCS, that we have integrated with a number of broadcast control vendors. So it's software that they interact with. They tell us what to do, essentially, saying, here are all your senders in your network. Here's where they enter your network. Here's the bandwidth of all your senders. So that's what you do when you create your broadcast, when you're creating your database, your routing database. So that those same steps apply. But then it tells us, again, all the senders in the system, and it also tells us all the receivers in the system. So what happens here is that the broadcast controller knows that camera 1 will have an IP address of 239.111, and the sender will be, say, leaf 1 interface 1. We want to route that to receiver 1, which is located on leaf 10 interface 8. So they will tell us, the broadcast controller tells us when an operator pushes receiver 8, camera 1, they'll send the command to their receiver saying tune to this specific multicast address, but they also send a command to our broadcast controller, to our orchestration service, MCS, saying route this from this switch interface to this switch interface, and then MCS will program those switches in a static fashion to program. So going across leaf spine leaf.
Maybe I've missed something here, but so the switches, that's 3PP. And your software works with these switches, or you have an API, or
So we make switches too. Like Arista Media Control Service provides orchestration with Arista switches.
So I was wondering, is this all integrated with NMOS, or is it something that you have to go through some sort of a gateway?
So the initial APIs were derived off of NMOS. We extended NMOS APIs to provide multicast programming, and real-time streaming notifications is something that we implemented apart from NMOS, and it's all standard-based open APIs.
And are you contributing those modifications back into the AMWA process?
I don't think we are currently. We send all of our notifications back directly to the broadcast controller. So when they send the commands, they're also listening for certain subscription channels to say, hey, this flow succeeded, this action succeeded, this action failed. So that's where we provide the notifications to.
Are you, orchestration, is that trying to address products that can only work on a LAN? Like there are some devices that only can work in a LAN environment, and they make proprietary fixes with IGMP snooping and
So at least today, most of these systems appear to be within a single facility, but there is not. But there are topologies. There are systems where we will need to be sending traffic between multiple sites, for example, or between multiple trucks, as an example. I know it's still a LAN, but same idea. So between one site and another site, that's something that we can also do via orchestration, assuming that the number of based on the system the system topology and number of hops. Did you want to say anything about that? Okay.
So, with orchestration, we should be able to provide, even if the topologies are located across sites, or if we want to push things to cloud, or if we want to do cross-zone support from IGMP zones to or SMPTE zones, the Arista Media Control Service can provision routes across these multiple sites too.
But to add to that, the initial idea for MCS was to kind of assist the broadcasters in creating some sort of matrix of senders and receivers. So while the initial design was based on essentially replacing, converting SDI into IP locally at a single facility, it can easily be extended to, send content, into the cloud, for example, or from cloud to bringing it back to ground on-prem. So there's a lot of flexibility there.
All right, thank you, everybody.